So why do we run these kinds of programs? We could just stay home and read papers and try to reproduce the work that's in those papers. But that way you often miss a lot of things. You don't know why some other approach wasn't used and so on. So it's a very, very different experience to have the best people in their field in the world coming here, talking, doing things on the blackboard, talks which are 2 hours long, and they can have as many questions as you want, and so on. That's the sort of unique experience that that happens here. And one of those best people in their field is here tonight with us, Maya Fishbach. Her PhD is from the University of Chicago, where she had Harper Dissertation Fellowship. And then she was postdoc, as we call it, a researcher at Northwestern University, and then moved to Toronto, the Canadian Institute for Theoretical Astrophysics. More recently, she won Polanyi Prize in Physics. And so with these kinds of events, we sort of try to do what we do in our programs. You're here, you're hearing things, you know, from the horse's mouth, so to speak, and you get to ask them questions as well. So I hand it over to Maya, and thank you for doing this.
Great. Well, thanks everyone for coming. It's so great to be here. Yeah, I much prefer being in this climate in November than in Toronto, although Toronto is a great city. I highly encourage everyone to visit in the summer. And today I'll be telling you a bit about what I work on, which is learning about black holes with gravitational waves. And so before I tell you about what gravitational waves are and what black holes are, I just wanted to start with this visualization of the very first system that we detected in gravitational waves 10 years ago this September. So this is a very exciting time for gravitational wave astronomy. We just celebrated our 10-year anniversary of listening to black holes with gravitational waves. And so the visualization that I'll be showing here when I play the movie is two black holes. Each of these is roughly 30 times the mass of the sun, and they are orbiting around each other. They're a gravitationally bound binary, and as they orbit around each other, they're radiating energy, that orbital energy, in gravitational waves. And that is causing the two black holes to get closer and closer together until eventually they get so close together that their horizons touch and they merge into this bigger black hole. And so that was specifically the first event that we saw in gravitational waves, but we've now been detecting a whole bunch of these. But first, let me explain a bit about what black holes actually are. So as many of you may have heard, black holes are, simply put, the densest objects in the universe. So what I'm showing here is a photograph of a black hole. This is actually a picture taken by the Event Horizon Telescope of the black hole in the supermassive black hole in the center of our galaxy. So this black hole lives in the center of the Milky Way, and it's roughly 1 million times the mass of the sun, so more massive than the rest of the black holes I'll be talking about today. But black holes are all pretty similar. They're just what happens when you take any amount of mass and squeeze it enough. So if you take the Earth, for example, and manage to compress it until it was a fraction of an inch across, the Earth would also become a black hole. And these objects are so dense that nothing can escape from them. So, right, if I am standing on the Earth, I'm not this strong, but if I was stronger, I could maybe throw a baseball up. It's physically possible to throw something up in the air so that it escapes the Earth and it doesn't fall back. And if I shine a flashlight, the light from the flashlight can make it out of the Earth's gravitational field. But if you are standing within the event horizon of a black hole and you shine a flashlight, the light from your flashlight cannot make it out of the black hole, and that's why they're called black. And so the next ingredient to my title is gravitational waves. And so gravitational waves come from Einstein's theory of gravity. That is a young Einstein. And before Einstein's theory of gravity, we thought of gravity since the 1600s, according to Isaac Newton's description, where gravity is what makes apples fall from trees onto the ground. We thought of gravity as this force. But Einstein gave us a much more elegant interpretation and changed our view of gravity. And Einstein's theory of gravity, known as general relativity, it tells us a new way to think about the very fabric of our universe. So according to this theory, space, so three-dimensional space and time, are linked together in this concept called space-time. And space-time it's this four-dimensional thing, space plus time. Here, it's much easier to visualize in 2 dimensions. So this is just a simplification of 2 dimensions. And it's this fabric that makes up the entire universe. And what gravity does is it creates this curvature in that space-time. So you can imagine an object with mass, such as the Earth, as bending space-time in this way, much like if you stretched out a sheet of spandex and you put a bowling ball in it, that would cause a dip in your sheet. And now if you had a little marble, I sometimes do this demonstration, right? You would see the marble fall towards that. So the marble is just moving on a straight line, but because gravity is bending the fabric that it lives on, it is so-called attracted towards the bigger mass. And so space-time tells matter how to move. So this curvature, these valleys in the fabric are telling other masses how to move. But matter also tells space-time how to curve. So gravity is linking the fabric of our universe with the objects that live in it. And now gravitational waves enter the picture. So this is a static idea here, right? Where we have the moon and the Earth each have their gravity. They're causing these valleys in space-time. But now imagine that your masses are moving. And so we know that in physics, information cannot travel faster than the speed of light. And so we need some way for those masses that are moving to communicate to other masses in the universe that the geometry of space-time has changed. They need to be feeling a different gravity. And that carrier of information in gravity is the gravitational waves. So you can imagine, for example, a bug, a water bug on a pond. That's the massive object here. When it moves, when it walks across that pond, it will create these ripples around it that propagate out that information. And so when these massive objects move, they cause ripples in space-time. These ripples are the gravitational waves. And so here is a different visualization of that very first gravitational wave detection of 2 black holes. They are orbiting around each other and radiating these gravitational waves that are bringing the 2 black holes closer and closer together. And now you can see the gravitational waves are represented as these ripples that travel out from the source across the universe and eventually reach us here on Earth. And these gravitational waves are a real thing. This is not obvious. So actually, for decades after Einstein wrote down the theory of gravity, and there were these things that emerged from the formula that were gravitational waves. People were not sure whether, mathematicians and physicists argued about this for a long time. Einstein actually didn't believe gravitational waves were a real physical thing. It turns out they are. We knew this theoretically, and we now, as of 10 years ago, know this by directly detecting them. And what I mean by gravitational waves being a real physical thing is that they actually create a physical effect. They do work on something, and we can measure it. And so as gravitational waves, for example, from those two black holes pass over the Earth, they will cause the Earth to slightly deform in this way, to stretch and squeeze. And here's those same gravitational waves passing over, frequencies increasing, the Earth is wobbling. Of course, the scale of this effect is vastly exaggerated here. Yes, the Earth does not turn to jello. And the reason for that, luckily for us, is that gravitational waves are weak. They really do not affect our everyday life unless you study them like I do, in which case they do. But yes, these gravitational waves are very, very weak. So in fact, loud gravitational waves, so like the loudest gravitational waves we can hope to detect, only change the distance between our sun and the next closest star, which is 4.3 light years away, by the width of a human hair. So it's a really, really tiny effect that is going on. And in fact, the actual changes in distance that we have to measure in our detectors in order to know that a gravitational wave has passed by is a tiny fraction of the smallest thing we can imagine, right? An atom, an atomic nucleus. The gravitational waves are causing a change in distance much, much smaller than that in our detectors. And so in order to actually detect gravitational waves, we need two things. We need a really loud source of gravitational waves, and we need a really precise detector. And so let me first talk a bit about the detector. So we saw a visualization of gravitational waves passing the Earth. Here's another way to visualize gravitational waves, where now I've imagined that we have this ring of what we call test masses, so just some little masses in a ring, and we have this concentrically a whole bunch of rings behind each other. And now as this gravitational wave is propagating through this funny little tube, it is causing each ring here to stretch and squeeze in this way as it passes through. And so this is the physical effect that we are trying to detect with our detectors, one of which is called LIGO, the Laser Interferometer Gravitational Wave Observatory. So instead of having a usual astronomical telescope, which many of us may be more familiar with, the way that these telescopes work is through interferometry. So each detector consists of these 4-kilometer arms, and at the end of each arm is a mirror, and that's what's shown here. This represents the arms, and these are the mirrors. And so instead of setting up a whole ring here that we can watch stretch and squeeze, we set up these mirrors at the end of these arms, and what we try to measure is the one arm stretching a little bit while the other one shrinks a little bit, because in this scenario, pretend a gravitational wave is moving into the screen or directly overhead or below the detector. And so we want to measure one arm stretching and the other squeezing, or the mirrors that are at the end of these arms moving relative to each other. Okay, so how do we measure that one arm is getting a little bit longer and the other is getting a little bit shorter? We can't just use a ruler, because if we had like a 4-kilometer stick, then that ruler would also stretch and squeeze due to gravitational waves. So what we use instead is we use light as our ruler. And the important thing to remember is that light always travels at the same speed. So if one arm is getting a little bit longer, it takes a little bit longer for the light to travel down the length of the arm. And if it's shorter, it takes a little bit shorter. And so I'm going to show this movie that is going to show a laser that is, passing. I didn't mean to do that. So the laser is passing through each of these 2 arms and getting reflected off of these mirrors. And that light is also a wave, right? So this light wave is traveling down this mirror, getting reflected back, and if no gravitational wave has passed through the detector, the light waves from the 2 arms just cancel each other out, destructive interference, and there's nothing at the output. But if the 2 arms are moving relative to each other because of gravitational waves, we have this pattern of constructive and then destructive interference as the 2 waves combine to cancel each other out or add up. And that causes the signal that we measure at the output. So that's how we use light interferometry as a ruler to measure relative changes in distance between the 2 arms. And these detectors are arguably some of the most sensitive instruments that people have ever built, right? Because they're sensitive to changes in distance that are this tiny fraction of an atomic nucleus. So 10 to the negative 19 meters is how tiny we're trying to measure distances, over 4 kilometers. Okay, so the next thing we need in order to actually detect gravitational waves is a really loud source of gravitational waves. So actually anything with mass that moves generates gravitational waves. I am generating gravitational waves right now as I wave my arms around because the gravity that my mass produces is changing a little bit. But in order to actually produce gravitational waves that we can detect, we need to focus on objects that are really gravitationally extreme, so really massive and dense, and moving at extreme speeds. And so merging black holes are a natural source of gravitational waves, and the only ones that we've detected so far. Merging black holes are neutron stars, which I'll talk a bit about later. So this is the movie that I showed at the very beginning. We've now detected hundreds of events like this, each consisting of 2 black holes that merge and emit gravitational waves in the process. And so when these 2 black holes merge with each other or coalesce, this is the distinctive gravitational wave signal that they make. So these are the 2 black holes. The first stage, where the 2 black holes are still relatively far apart, we call it the in-spiral stage. And then this is the corresponding gravitational wave. So it's a wave, so it has some amplitude and some frequency. And here the frequency of the gravitational wave is twice the orbital frequency of the 2 black holes going around each other. And then because the gravitational waves are emitting energy, the black holes get closer and closer together, and they're moving around each other faster and faster. And so the gravitational wave frequency also increases, and it also gets louder because the 2 black holes are getting closer together. So the amplitude also increases. And then eventually the 2 black holes touch. This is called the merger phase. There's a peak. This is the loudest the gravitational waves are. and then you just have one slightly deformed black hole that rings. It rings like a bell that's vibrating as it sheds off any residual weirdness. And it finally settles down into just a perfectly spherical black hole, no longer emitting any gravitational waves because it's just a perfect sphere that's not moving. And now I can play what the gravitational wave signal sounds like. So you may have noticed when I was introducing detector and source, it was like a microphone and I guess a speaker and a microphone. And so we often use the analogy of sound to talk about gravitational waves because we want to distinguish it from the way that we've been observing the universe for millennia before we had access to this technology, which is with light. So we like to say that it's like we've been watching a silent movie for all of these years and we finally turned up the sound. But there are other reasons for this analogy, one of which is that the gravitational waves we happen to be sensitive to right now are actually in the audio band. So you can plug in that wave that comes out of our detector and play it and listen to it in your ears. And that's what I will do now. So that first one where it's pretty low pitched and sounds kind of like a thump is the real frequencies of this first detection. It was pretty low frequencies because the two black holes were relatively massive. And then there's the second version that's kind of put up to a bit higher frequencies that's more within our audio band. And you can hear the kind of chirp as the signal starts off quiet at low frequencies and then moves up to higher frequencies and is louder. And actually, the way that our ears process this signal is similar to the actual search techniques that we use to distinguish signals like this from noise. So here you can see this signal was actually really loud above the noise, but there's a lot of detector noise that we have to pick the signal up on top of. And the computer algorithms we used called matched filter searches are very similar to the way that our brains can process a conversation we might be having in a crowded restaurant with lots of background noise. So that's another fun fact about the audio analogy. But let me move on to talking a bit more about the astrophysical applications. And so much like we have telescopes all over the world that are looking for light from different stars and galaxies and really fun things that we can see with electromagnetic radiation, we have this worldwide network of gravitational wave detectors, each one of which consists is this L shape with these two 4-kilometer arms for the two LIGOs. So we have these interferometers, LIGO in the US, in Hanford, Washington, and Livingston, Louisiana. There is a third detector with 3-kilometer arms, Virgo, in Italy. LIGO India is under construction and will come online sometime soon, probably early 2030s. And then Kagra, which is in Japan. And so these detectors all operate hopefully at the same time and listen for gravitational waves from across the universe. And here is a very, very crowded poster showing each panel shows every detection that has been published so far by the LIGO-Virgo-Kagra collaboration. So it's really hard to see because there are just so, like we've seen hundreds of these things and published over 100 of them so far, but each one of these little postage stamps shows a chirp of that gravitational wave signal. And of course, each one of those systems, this is just showing a subset of them, is coming from two black holes that are orbiting around each other. And so here's a nice visualization of those. The sizes of the circles here are proportional to the mass of the black hole, and you can see the really small ones move a lot faster at higher frequencies than the really big ones, for example. And so this is an amazing, amazing observational data set that we now have access to. And so here is another visualization of everything we've detected in gravitational waves compared to what we knew about neutron stars and black holes without gravitational waves through electromagnetic observations. So what this picture is showing is down here are all the neutron stars, which I'll talk a bit more about in a few minutes, that we knew about before gravitational waves just by observing them often in our galaxy. You may have heard of things like pulsars, for example. Here are the black holes that we can detect without gravitational waves. Often they are accreting something that is releasing energy and making them glow in some way. None of the light is actually coming from the black hole, but they are doing something that is that makes them able to observe them in light. They're emitting some kind of light. And then in blue and some in orange is everything we've detected in gravitational waves. So the position here on the vertical scale is telling you how massive each of those objects are. So the things up here are over 100 times the mass of the sun, and the things down here are around 1.5 times the mass of the sun.
What's the horizontal axis?
The horizontal axis just makes it look cool. I don't know, it's some kind of Rorschach test, what you see in this. Yeah, and so whenever we detect a gravitational wave source, we actually detect 3 black holes, right? There are the 2 black holes that merge with one another and then make a bigger black hole. So that's why there are these arrows representing each gravitational wave source. So one thing you can see is that we know of way more black holes in the last 10 years through gravitational wave detection than we knew for the previous several decades that we knew that black holes existed in our universe and looking for them just with light. So this is a really powerful probe of finding black holes in our universe. And one reason why we use this sample, and we're really excited about this sample, is here you can see its masses in the stellar graveyard. So we think that a lot of these neutron stars and black holes are the remnants, the skeletons of massive stars. And here's a cartoon of a massive star that lives its life on an astronomical scale. These things live for a really short time, right? Only 10 million years or so. That's the blink of an eye for astronomy. And then they die as a supernova and leave behind these black holes. And so these massive stars are very rare and short-lived in our universe, and so we don't know a lot about them. They're kind of elusive, but we know they're really important because they shine really bright, they shape their entire galaxies, and even though they live for a short time, the black holes or neutron stars they leave behind just persist throughout the universe. And so studying these skeletons is a good way to learn about the lives and deaths of the stars that came before them. And so one of the things that we want to learn about, we often refer to this as like gravitational wave paleontology, in analogy to using dead stuff to learn about the things that came before. So we want to learn about these stars from their black hole skeletons. And one of the things that is really not obvious at all is how two stars lived their lives and ended up becoming a merging black hole system. So before we discovered the first gravitational wave detection of two black holes that merged, we had no idea that these types of objects existed. And since then, of course, we now know that they exist, and there have been a lot of different ways that theorists have come up with explaining how this could work. This is just a simplified version showing the isolated formation channel, as we call it, when you just start off with two stars that have lived their entire lives together. They die one by one and form these two black holes that are close enough together that they'll eventually merge within the age of the universe. So this is like a very romantic little marriage of these stars, versus another type of environment is where you start off with a whole bunch of stars in some dense cluster of stars, sometimes called the globular cluster. If you've heard of those, these are very dense regions that can contain millions of stars that die and make this cluster of black holes, kind of like a mosh pit of black holes that just interact with each other and randomly find another pair and assemble these tight binaries that merge. And so these are like the types of questions we want to answer. Is did these two black holes come from two stars that were always together, or did they just find each other 1 in a million in some kind of dense environment? And there are lots of ways that we have looked at the detections and analyzed them and tried to understand, which systems came from which sorts of environments. But hot off the press, I think last week, the LIGO-Virgo-CAGRA collaboration published this new event. We name our events by GW for gravitational wave, and then the date at which they were detected. So this one was detected in 2024, I guess almost exactly a year ago. And we just published it. This is actually really fast for us. We take a long time to do our analyses because we're very careful. But this was a discovery of a black hole merger with unusual spins that is very informative about the type of environment that it came from and the type of prehistory that it had. And so what we mean by unusual spins here is that this one, there's a big black hole here and a kind of smaller black hole that's around half its size of the bigger one. And most of the black holes that we've observed, so in addition to how big the black holes are, we can also study how fast they're rotating. So black holes can also be rotating. And the rotation of the black holes, we often can't really measure, are the black holes rotating clockwise? Are they rotating counterclockwise? And in addition to the rotation of the black holes, we know that the black holes are going around each other. So the two black holes could be rotating around each other in a clockwise way, in which if those two black holes came from two stars that lived their whole lives together, we might expect the two black holes to also be rotating clockwise. We'd expect things to kind of be synchronized because they've lived their whole lives together in this pair of stars. They probably kind of informed how the other one is rotating and also how that's related to how the two black holes are going around each other. In this event, this merger of two black holes, we know that at least one of those black holes was rotating opposite to the way that the two black holes are going around each other. So if they're going around each other clockwise, one of the black holes was going counterclockwise. And that is much more likely to happen if you have your two black holes finding each other randomly, where they don't know what the rotation of the other black hole is, what its spin is, because they've just found each other in this dense environment. So this detection that we published last week kind of hints that this system came from some kind of dense environment like this, rather than the two stars living their whole lives together. So I've talked a bunch about black holes. Another type of compact object or stellar remnants that we detect are neutron stars. I won't talk about these as much because we just haven't seen as many of them. We've only seen a handful of gravitational wave mergers involving neutron stars. But neutron stars are very exciting. Even though they're less dense than black holes, they're still denser than anything we can imagine here on Earth. And they're actually made of stuff. So they are made of, they're basically an atomic nucleus that has been supersized up to 1.5 times the mass of the sun, but compressed down to a city scale. So only like 10 kilometers across. And so the stuff that makes them up, the neutrons and protons that make up these neutron stars, are at very, very extreme conditions. And we had this one amazing gravitational wave event almost 10 years ago now, in 2017. But I'll just spend a few minutes on it because even though it was so long ago, we're still extremely excited about it and still actually learning new things from it. And so when two neutron stars merge, unlike black holes, the neutron stars actually have stuff inside of them, and they make this cosmic explosion across the electromagnetic wavelengths. So here we start off with these two neutron stars that merge. There's these jets of gamma rays that get emitted that we can detect. There's this explosion called a kilonova. And for this one event in 2017, in addition to detecting the gravitational waves, we detected light across all of these wavelengths, from the highest energy light all the way down to radio waves from this one system. It was extremely exciting. One of the reasons it is exciting is because it showed us that merging neutron stars make some of the heaviest metals in our universe. So things like gold and platinum. Here's just an astronomer's version of the periodic table from high school chemistry, which is now colored by the types of astronomical objects that make the different elements. And so merging neutron stars here are all the things in yellow. So you can see they make some of these heaviest metals. This one, our best estimate for this one event from 2017 is that it made around a few hundred Earth masses in gold, which is pretty cool. It was 100 million light years away though, so I don't think we can get any of that gold, but it's made us rich in knowledge. Sorry, that was cheesy. Okay, another thing that I do in my research that is made much easier when we have these merging neutron stars is to try to address some of the biggest questions about our universe, such as how old is the universe, right? And so one of the ways that we try to understand this is we know that the universe is expanding, but we don't actually know at what rate it's expanding, even though we've been measuring this for 100 years. So we try to measure the expansion speed of the universe as a function of distance. So things that are, the galaxies that are further away are expanding faster. And with gravitational waves, they're very unique because they directly give us the distance to the source. So with normal astronomical observations, it's very hard to know how far away something is, because if you see a really faint galaxy, you don't know, is that galaxy just kind of a faint galaxy, or is it a bright galaxy that's really far away? With gravitational waves, we can break that degeneracy between how loud the gravitational wave is and how far away it is, because the frequencies of the gravitational waves tell us how bright it is, and so how loud. And so how loud it looks in our detectors just tells us how far away it is. And so we get this really, this distance to the gravitational waves really well, that we don't need any kind of additional calibration other than the theory of gravity and the calibration of our detector. And if we have some way of estimating the speed at which that source is moving away from us, that allows us to put a point in this Hubble diagram. And so when we know what galaxy it came from, we can measure the redshift of the galaxy based on the spectrum of the galaxy and the chemical fingerprints that get redshifted as the universe is expanding and the light from the galaxy is getting stretched out. So that's another fun application. And now, just to conclude, hopefully I've convinced all of you that there's a lot to learn from gravitational waves. We're still just getting the tip of the iceberg with our first few hundred detections over the past 10 years. They carry information about the motions of massive objects, collisions of black holes and neutron stars produce loud gravitational waves. There are probably other things that produce gravitational waves that we might detect one day, but it's only been 10 years. So this is what we've been detecting so far. The way we detect them is with interferometers like LIGO, Virgo, CAGRA. By analyzing the gravitational waves, we can measure how big the black holes or neutron stars are, how fast they're rotating, and also in what direction they're rotating, and how far away they are, and a bit about where they are in the sky. And when we have a whole astrophysical catalog of these black holes and neutron stars, that allows us to learn about their prehistories, the stars that came before them, the origin of heavy elements, the age of the universe, and also make unexpected discoveries. So thanks everyone for your attention, and I'm happy to take any questions.
Questions, yes. Craig is bringing you a microphone, so we can hear you.
What's the frequency of neutron star collisions? You're saying they're pretty small, and so how often do they collide? I mean, is that a frequent event in the universe, or?
Yeah, that's a great question. So that is one thing that we estimate. We know what our detection rate is, which is much lower than the detection rate of black hole mergers. We've only observed probably 2 merging neutron stars compared to a few hundred merging black holes. We've also observed some mixed, like a neutron star merging with a black hole. But we actually think that in the universe, neutron stars merge around a few to maybe 10 times more often than black holes merge. And the reason why we've detected so few of them comparatively is because the gravitational waves they emit are quieter. And so we can only detect the neutron stars that merge closer by, whereas we can detect black holes out to further away. And so we probe a much larger volume of the universe where black holes could be merging.
So how frequent would these collisions be? I mean, happening every year or every
So what saves us is that there are lots of galaxies in the universe. So per galaxy, we think neutron stars would only merge like 1 in 10,000 years, and black holes only merge 1, or 1 in 100,000 years. Black holes maybe merge like 1 in a million years, kind of like that kind of scale. Yeah, but there are so many galaxies, and that's why we're able to detect black holes merging every day.
Yes. Great, right there. Okay.
Yeah, can you say anything about dark matter from your measurements?
Yeah, that's a good question. I think there are a few things. One thing is that we're not totally sure, well, we kind of have no idea what dark matter is. And so one theory of dark matter is that actually black holes could be making up some of the dark matter. And so one of the things we're able to study is by observing this big sample of black holes, we can try to understand, is it possible that black holes are making up some of the dark matter? Probably the majority of the black holes we've observed are not dark matter, but it is something that people are trying to understand. So this will be an alternative to these black holes coming from dead stars, as they could actually be coming from primordial density fluctuations in the early universe. Another thing that we might hope to do, mostly with future gravitational wave detectors, is be sensitive to the environmental effect that dark matter would imprint on the signal. So for example, because dark matter has mass, it's also affecting the gravity of the system. So if these black holes are merging in some very dense dark matter environment, the structure of the dark matter could be imprinted on the gravitational wave signal. But that's something that we would probably need future detectors to really find.
Can you?
How can you tell from the merging of two black holes how far that merging happened, and what's the furthest event that you've detected?
Yeah, great question. So the way that we can measure how far away they happened is really by what the amplitude of the signal is. So is the gravitational wave loud or quiet? That is, as I just explained in the difference between neutron stars and black holes, that also depends, the intrinsic loudness of the gravitational wave depends on how massive the two black holes or neutron stars are. But we can get that by examining the frequencies, because the bigger black holes also are at lower frequencies. And so by looking at the frequencies, we know how intrinsically loud the gravitational wave source was. And so if it, based on how loud it is in our detectors, the amplitude of the gravitational wave decays inversely with distance. So things that are 10 times further of the same masses are 10 times quieter. And that's how we get the distance. As far as the furthest thing we've seen, I don't have that number in convenient units, but it is it is roughly, if this means anything to you, it's redshift of around 1.5. It is when the universe, it's roughly corresponds to a merger that happened 8-ish billion years ago. So, you know.
Hi. These are ripples in space-time, right?
Yeah.
Okay, so I'm thinking, atomic clocks are really, really accurate now. Could we, I'm just thinking, maybe put like 4 or 5 atomic clocks three-dimensionally apart and then watch the changes in time relative to each other as the gravity wave goes through? Have they thought of that?
Yeah. I mean, so like space and time are kind of the same. Like we can we can always translate between space and time using the speed of light. And so that is actually a really excellent question, because another way of detecting gravitational waves that I didn't talk about is what's called pulsar timing arrays. And so we don't have to put these atomic clocks out in the galaxy, because the galaxy has already done that for us with these millisecond pulsars, which are neutron stars that emit these rays of light, and that they rotate, and so the rays hit us at very precise intervals because the rotation of these stars is so stable. And so like once a millisecond, we get a pulse from some of these fastest pulsars. And through timing the arrival times of these pulsars, which are spread across our entire galaxy, we can detect much, much lower frequency gravitational waves than what I was talking about here.
I had one more, it might sound like a joke, but it's not. We depict in your two-dimensional picture gravity well, going down. And then gravity waves are plus and minus the average. So on a peak of a gravity wave, would it be repulsive gravity?
Yeah, it's not. So it's not really repulsive gravity. That is, I think the ripple, I guess the ripple analogy only gets so far. But yeah, no, I have it. That's a really good question. It's mostly the effect that it has. Like the effect is not so much a change in the gravitational field as in the change, like we treat these things as small perturbations on top of some background gravity. So they're way too small to really like affect the overall structure of the space-time, but they're really just causing these very small deformations on top of that space-time. So they're just like very, very tiny in this regime that we're considering here.
A subatomic particle maybe wouldn't see it as interpreted as repulsive gravity?
I mean, it's causing that particle to move in some way.
Can you speak to how the LIGOs give you directionality to the mergers? I mean, you said sky location, and I wrap my head around how the one interferometer gives you amplitude and frequency, but how do you get directionality?
Yeah, so with one interferometer, you can't really do it well at all, because the great thing about these detectors is they're kind of all sky. They are sensitive to anything that is broadly above the detector or below the detector, so that's a huge fraction of the sky. The main way we get localization is by having, when you have two detectors, then you know the arrival time difference, and so that traces out like a circle in the sky. When you have three detectors, then often that narrows it down to a point, so because of the timing, the triangulation.
Obviously, you're improving these detectors, over time. When is the next big improvement in LIGO sensitivity?
Yeah, so we've been gradually improving them. Oh, sorry, I pressed some button. And so they've been getting better between every observing run. We are currently observing for another couple weeks, and then the observing run after that will start in summer, fall 2026. So we'll be hopefully like a few times more sensitive then. Really the next big thing to improve the sensitivity a lot, like by a factor of 10, is to build new detectors that instead of 4-kilometer arms have 40-kilometer arms. So that'll be the next, like we can pretty much keep all the technology the same, just increase the arm length by a factor of 10, and that pretty much automatically increases the sensitivity by a factor of 10.
Is LIGO, Virgo, and Kagra the same technology? They're all identical, or are they different?
They're not. The LIGOs are identical, so the two LIGOs in the US and LIGO India are identical. The other ones are a similar idea, but not totally identical technology. So there is different complementary technology that's being developed.
Which is the most sensitive?
LIGO.
Let's take one final question, but we can continue up here afterwards, if there is one. Right here.
Yes, each detector has two arms. Would there be anything gained on building it on top of the mine or drill a hole and have 3 perpendicular arms?
I think that would just be really, really hard, because then you'd have to, you'd also have to, that arm would experience changing gravity due to the different distance from the Earth. There are 3, like you could do a triangle, which kind of is like another arm, and that gives you different combinations of the arms than you can get with just an L. And there are some detector designs. I mean, the one that is actually happening is a triangle in space. That's called LISA, which I didn't talk at all about. But yeah, I think trying to build something vertically on the Earth would be too challenging. I mean, also because it's really heavy, but also because of the change in gravity you would experience.
Thank you once again.